Hello and welcome back to another episode of the Oxford Online Maths Club. No problems here ever at all on this live stream. Today I'm joined by current second year student Isiad. He's been on the live stream twice before. Zero errors. Very professional live stream. He's been live streamed twice before to talk about complex prime numbers and also to talk about Olympiad problems in seasons 2 and 1 respectively. Coming up today, we've got a session on inequalities, which we'd like to do, and possibly other stuff as well. Say hi to Hussein and Jonah in the chat, please. Jonah, I think you've met before. Hussein, I think it's Hussein's first time moderating in chat. Chat is appearing on screen below and going past super fast. Hi to people who I can see on screen, which is Manya and an anonymous person, and Joe and Dan, Ali and Raphael and Alfie and other people in chat as well. Hi, nice to have you with us. Hi Harriet and Ramanajan. The rules for chat are that you can be anonymous if you want to. You don't have to put your name in. We're using Slido over at slido.com/OOMC because you don't have to log into YouTube to use Slido chat. Molly's here and Wyatt and Yago. And Alex is here as well. Nice group of people, brilliant stuff. Great to have you with us. Further reading for each episode of the Oxford Online Maths Club is posted on the website at www.maths.ox.ac.uk/art/club. When I remember to do that, there are zero mistakes on this live stream. It is a mistake-free zone. Right, okay. Obviously that's not true.
That, enough times you will convince them. So
yeah, if I say it enough times, then it might become true. Right, okay. Let's get rid of this, and maybe I'll just shut up. And I'm going to hand over to Isiad to tell us about inequalities. Over to you.
So today we're going to talk about real number inequalities, and one of the fundamental inequalities we have is that some square number is greater than or equal to 0. Every number, if you square every number, it's greater than or equal to 0, and from that we get a really cool thing, which is the AMGM inequality. And we'll see in the slides that from those we can get far more stronger inequalities and solve some problems with that. Right. So as I said, the AMGM inequality. Well, what does AM and GM stand for? So as you can see on the slides, AM is the arithmetic mean, which is basically just adding the numbers and then dividing by how many numbers they are, which all of us are familiar with. And then we also have the geometric mean, which is what you get when you multiply all the numbers and then take the root. In this, for two numbers, we have the arithmetic mean is a plus b over 2, and the geometric mean is square root of ab. And there's a really nice geometric proof of that, which I think we have on the next slide, or on this slide, yeah. So basically, what you do is that you take a segment with sides side length a plus b, as we have it's capital the segment capital AB, not confusing at all. But yeah, that has length a plus b. And then we draw a semicircle with diameter AB, and that semicircle has radius a plus b over 2, which is the red line that I've drawn, and that's the arithmetic mean. Now,
Okay.
In order to show that the arithmetic mean is always greater than or equal to the geometric mean, I claim that the green line is the geometric mean. And if it is indeed the geometric mean, then it's kind of obvious that that has to be less than or equal to the arithmetic mean. Now, how can we actually show that? Well, if you know your geometry kind of well, then you'll remember that angle ACB has to be 90 degrees. And then we have, since CD is a perpendicular from AB, we have a bunch of similar triangles, and from those similar triangles we can do some ratio chasing, I think.
Shall I have a go at it?
Yeah.
I'll have a go at the screen. We had this as an option that we weren't sure if we were going to do it. I can try and attempt to do the geometry puzzle. It's a bit weird, isn't it? There's a algebra fact that you're going for.
Mm-hmm.
You're going for this kind of purely algebra fact. It's bigger, right? Bigger than or equal to square root of AB. But there's a geometry way to do it by drawing a very particular semicircle. Okay, so you already described the first bit, which I'm going to try and do. By the way, more people have joined chat. Cicero's here, and Danny B and Raf. Danny remembers Itiad from a previous episode and says, "Hi, Itiad." Cool. Okay, so this is your picture.
Mm-hmm.
You've got this semicircle with A. I can't remember what these points are called. Not really important. And this length B. So the diameter is A plus B. So the radius. If I try and find the radius, so I don't know if this is the middle of the middle of the circle, then this radius is A plus B over 2. So that's relevant because that's the left-hand side. And then you claim that this line here, this height of this bit, where it splits it A and B into unequal parts, that bit's root AB, and that I can just do similar triangles to find it, right?
Mm-hmm.
Okay. I'm talking slowly in case anybody wants to try this on a bit of paper at home, and also to buy myself some time to remember how similar triangles work. Okay. So we can draw in lines like that, and I want to do that because there's a right angle in a semicircle. Yeah, right angles in semicircle, and I've got a right angle here. Let's draw that one bigger. Okay. So, what can I do? Well, I suppose I don't know this height x or something.
Yeah.
I want to find x. And I've got a triangle on the left. I can see this one. I sort of hope that this one's similar to the bit on the right.
Mm-hmm.
I think it might be. There's some angle up here, I don't know, alpha or something?
Yeah.
And then this is 90 degrees minus alpha. Aha! This is also alpha.
Yeah.
Some angle chasing has happened. And I've got a similar triangle over here. Okay, these green triangle and the blue triangle are similar. So what is this? X over A. X over A is equal to, I've got to turn my head sideways, B over X.
Mm-hmm.
Aha! So I can solve that. Solve that to get X squared equals AB. I think I've done it. X is positive.
And then X equals to AB.
Okay, which is the thing on the right hand side, which you said was called the geometric mean.
Mm-hmm.
Oh.
There's a question in chat, like why is the geometric mean root AB? I'm not exactly sure, but I think the answer to that is like, if you have a rectangle of like side lengths A and B, then the square which has the same area as that has side length root AB, and that's like a geometric interpretation of this thing.
Sure.
I believe that's why it's called the geometric mean, but I'm not 100% sure.
I've seen it come up in other problems with similar triangles as well. It's worth stressing, so that on the left it's A plus B divided by 2, and on the right it's A times B to the power of 1/2. So it's sort of like multiplication instead of addition, and powers instead of multiplication.
Yeah.
There's power of 1/2 instead of multiplying through by 1/2. So it's a little bit weird. It's like the next step up. The big triangle is similar to the smaller two. I didn't use that fact, Ali. It's true. None of its sides, well, one of its sides is interesting to me because it's A plus B. The other sides of the big triangle I wasn't that interested in, so I didn't write down similar triangles for it. But true. Yeah, Raphael says it's like the arithmetic mean but with multiplication, I guess, in this sense. There's like, you sort of twist your brain until you replace all the addition with multiplication, and if you've done that, then instead of dividing, the right thing is kind of square roots.
I mean, if you take the log of one of the sides, it becomes an arithmetic mean. But
Oh,
that's
goodness. How much do people like logarithms in chat? I can't remember. How do we feel about logarithms, chat?
but yeah, no, that's a spoiler to something we're going to do in the future in a bit.
Okay, that's a spoiler for later in this session. Okay, well, no spoilers.
But yeah, so yeah, log of root AB is like log A plus log B over 2, right?
Right, yeah, okay, so that splits out again if you know some logarithm facts. An anonymous person in chat has suggested the intersecting chord theorem. We talked about this in the practice session, whether they would know the intersecting chord theorem or not, and
Yeah.
turns out at least one of them does. Dan studied logarithms today. And some thumbs ups for logarithms. If you like logarithms, try expanding this logarithm into nice simple terms. You might get a surprise. Right, okay. I've done your geometry puzzle. I've worked out that the height of this point is root AB, and the punchline is that's smaller than the kind of maximum height of the semicircle, which is the radius. Okay, right. I'm going to put this right and let you get back to your slides. Oh, that didn't work. Cool. There it is again. So there's that picture with the geometric mean, with the square root thing that I found, and the arithmetic mean just being the radius, and the semicircle shows, aha, radius is bigger. So this is the big side round. People are multiplying out logarithms in chat. Good job, everyone. Okay, well, so cool fact to do with A and B.
Yeah. But it turns out that like the arithmetic mean, this inequality holds for multiple variables as well. Like we've shown the proof here for 2 numbers, but we can easily extend this to multiple numbers. I think that's on the next slide.
Yes, okay. So this is a little bit scary, isn't it? But this is
Yeah,
the
this is
same.
slightly scarier, but also like it gives us more power. I think that happens in maths. Like you get scarier stuff, which gives you more power, and then you're really powerful.
Also,
I mean, that's
the
how
more,
I like to think of it. Well,
if you absorb all of the scary maths, then you can become more powerful than it. Okay, let's take this in slowly then.
yeah,
This is a generalization of the thing from the previous slides, your AMGM inequality. Any number of variables, and you're calling them, instead of A and B, A1, A2, A3, A4, up to AN. So there are n of them, I guess. And the general rule is the arithmetic mean is the thing that maybe you learn in statistics in school or something. Add them up and divide by n. Whereas the geometric mean is multiply all of them. I guess these are all multiplied together. And you take the nth root. There's a tiny little n on this root. I don't know if people can see it at home, but I've read it out now.
yeah.
Okay.
And like this inequality always holds, but like if all the number we have an equality if and only if all the numbers of a1, a2, and all the subscripts are the same. Like all the numbers are the same. If you go back to the previous slide, like we can see that happening for 2 variables. If we had a and b equal here, then the green line would coincide with the red line, and we would have am equal to gm. And that bits like that shows that claim is true. But not in the case of n equals to 2, we would need to prove that, but it's not what we're aiming for today. So we're going to skip the proof of the general AMGM. Like the normal proof of the general AMGM, we might do something else. But yeah, if you're familiar with induction, you can prove this statement using forwards backwards induction, which is like a really neat technique of doing stuff. But we're not doing that today.
There's a suggestion in chat to try doing a 3D version of the picture that we just had before, to use 3 dimensions. Chat loves having higher dimensions. I don't know if that works, or I'm not even sure I know entirely how that would work, but I think it's the sort of thing you should try at home. So whoever suggested, it's an anonymous person, so it's kind of all of us, suggested proving it in 3 dimensions. Sure, have a go. Even if you don't prove AMGM, it sounds like a fun sort of thing to try. Okay. And there's some method of forwards backwards induction that I might put in the further reading to prove this general statement with n variables in. But, next slide.
AMGM, like we have a couple of examples here. Like AMGM implies that a squared plus b squared is greater than or equal to 2ab. And that's you can see that by plugging in the terms a squared and b squared instead of like a1 and a2, and then just multiplying by 2 on the right on both sides to get this. We can do the next example we have is like a cube plus b cube plus c cube is greater than or equal to 3abc, and we can get that by using the three variable version of AMGM. But what the important thing here is that AMGM allows us to have many different kinds of polynomial inequalities where we have a polynomial on the left-hand side, a multivariable polynomial, which with a, b, and c's and so on, and polynomial on the right-hand side, and we can like come up with many kinds of inequalities. We have a bunch of examples to like solve some inequality problems next, I think. Yeah. So we have two examples here. Now, do we want to wait for a bit and like let them have a try?
I think that sounds like a good idea. So part of the fun of being shown something like the AMGM inequality, with all of its big generality, you're allowed to put n different things in, and you can choose what the things are, so long as they're non-negative. It's sort of like a factory for just building your own inequalities. So there are some examples, some sort of target inequalities on the board. You can aim for those if you like, or if you want to practice, then just plugging stuff into AMGM is quite good fun. So I think let's give people a minute to go.
I like to think of solving inequalities as like building up arsenal. Like on the previous slide, we had a squared plus b squared is greater than or equal to ab, 2ab. And for the first example, we have something similar. We have a squared plus b squared, but we also have c squared. And we also, on the right-hand side, we also have bc and ca. So for the first inequality. And so we might try something like adding up a bunch of inequalities that we can produce by doing AMGM.
Right, okay. Let's give them a minute. So my first guess of things to plug in would I think be a squared, b squared, c squared, because it's the thing on the left. To plug those as my three things. But then I think I don't know if anybody's got this at home as well. If you plug that into the AMGM inequality, you get a squared plus b squared plus c squared divided by 3 is bigger than or equal to the cube root of a squared b squared c squared, which is not quite the thing on the right hand side at all. But hey, it's true.
Yeah, it's not. On the right hand side, we have like stuff that's multiplied by. We have stuff that's like multiplied by only two variables. So that would mean we could. We probably should try something like some AMGM with just two variables and then adding them up like cyclically. There's a solution in the chat which uses a really nice square trick. But like this is what this is a really nice thing, because like every problem you can solve with AMGM, you can also like theoretically solve with making everything be square numbers on one side and greater than or equal to 0 on the other side. So that can be done. I think U sub has the solution there.
It's something clever that's a bit like completing the square.
Yeah.
But you said something about adding together different inequalities. This is kind of like you're gaining power by combining together different inequalities.
So yeah, from the previous slide, we had that a squared plus b squared over 2 was greater than or equal to ab. And if we do the same things for the other two variables, if you do the same thing for the other two variables, we get this. So we have a squared plus b squared over 2 is greater than or equal to ab, and then the same thing for the other two. And if we add all of those up, on the right-hand side, we immediately get ab plus bc plus ca. On the left-hand side, we get a squared over 2 plus a squared over 2 plus b squared over 2, and like so on. So on the left-hand side, we get a squared plus b squared plus c squared as well. And a similar but slightly trickier thing happens for the next problem, which is like on the right, the one we have on the right-hand side. It's a to the power 4 plus b to the power plus c to the power 4 greater than or equal to some other thing, which I don't want to say it out loud. Yeah. And the trick here is also quite similar. Like we have we take one of the expressions on the right hand side and we experiment with something that could give us that could have a geometry mean that is equal to that side. Like we have one of the terms we have is a square bc, and since that's on the lower side of the inequality, we we want that to be the geometric mean of something, and we would ideally want something that has a to the power 4, b to the power, and c to the power 4. Um, and if you work with like sorry, I was just reading a comment. If you work with the like coefficients for a bit, like adding 2a to the 4 instead of like just a to the 4, or 3a to the 4 instead of just like 3b to the 4 plus c to the power like 5 3c to the 4 or something, like and then divide by all the times you've done that, you get a different expression on the right hand side each time. So yeah, like if you experiment for a bit, and then you get the right thing, and then you add all of them up, and that solves the problem basically. Which is quite like it's quite a powerful trick. It allows you to solve like almost all polynomial inequalities that are actually true.
Almost all inequalities that are actually true. I love it. I've realised we're looking at these problems in quite. You and I are looking at the problems in quite different ways, because when I see questions like this, I find myself looking at the left-hand side, the simple left-hand side. So I was imagining putting these into the plus bit of AMGM, the kind of bit on the left with the pluses. Kind of recognise the shape and think, aha, this looks like the pluses on the left. Whereas I think you were maybe thinking about the right-hand side and these items a squared bc, and maybe you can see some symmetry going on, some sort of repetition or cycling of the letters. Because I suppose on the left there's lots of ways you can make a to the 4 b plus b to the 4 plus c to the 4 on the nice arithmetic mean side where you're just adding things and dividing by numbers. But on the right-hand side it's pretty hard to land on an a squared bc on the right.
So like the a square bc restricts the amount, like the possibilities we have. To get a square bc, we would need 2 lots of a to the power 4 and 1 lot of b to the power 4 and 1 lot of c to the power 4, and that basically gives us the intuition of taking this expression we have on the left hand side. Yeah. Because this is not obvious. Like why would we take 2 times of one amount and then 1 times of the other ones?
Yeah, I mean, there's clearly 3 things on the left when I look at the left, but you're somehow, I think, looking at the powers and thinking, the powers add up to 4, so this feels more like a 4-item AMGM sort of thing. Ali in chat says, it feels obvious now you see the solution. And I think I agree. Once you've seen Itiad's solution, with this really clever idea to put a to the 4 in twice, then it does work out. But it's kind of different ideas about how you get there. I think there's 2 things going on. I think it's this idea about trying to make a squared bc out of going back a bit, out of this right hand side bit. There's an idea there to repeat an a to the 4, and also just the idea to use a to a big power, a to the big power, b to the big power, c to the big power, so that this nth root doesn't appear in our final answer. If you put a to the 4, a to the 4, b to the 4, c to the 4 inside here, then the fourth root just doesn't make things hideous. Mm-hmm. So I think it's pretty good. And Alfie's learned we can add inequalities together. Yeah, if you've got three different big things, 3 different small things, then the sum of the big things will be bigger than the sum of the small things. You can check that by checking that the difference between the sum is definitely positive, I guess. Positive by the sum of the bits. Are people being nice?
Difference is always non-negatives, and if you add non-negative numbers, they stay non-negative.
Cool. Good. So someone anonymous said, I don't get the solutions, which is fine. Let's look at the left one. It's kind of 2 separate problems, isn't it? There's a left problem, and entirely separately there's a right problem.
These are 2 separate problems. I just put them all into one example because, you know.
Yeah, maybe this could maybe have been 2 slides. But anyway, on the left, there's this idea to take these things that AMGM gives us, like a squared plus b squared over 2 is bigger than or equal to ab. That's true because of the AMGM thing, putting in a squared and b squared. And to take these other 2 versions of it, and then we can add those together to get something new and cool, like this thing up here, where on the right I've got AB, a BC, and a CA from adding these things together. On the left, all the 2's go away because I've got a squared over 2 twice, once over here and once over here. So the factors of 2 in our working out here go away over here. So it's pretty nice. On the right, it's a slightly more complicated idea, using these 3 things, which are each true by AMGM on 4 items, a to the 4 plus a to the 4 plus b to the 4 plus c to the 4. And on the right, plugging those things into 4th root. Good. Someone anonymous in chat who's being nice and helpful is explaining about adding inequalities together, which is not obvious. So yeah, good. Okay. Learning, good. Right. Okay.
I think it was one of the axioms of real numbers when we did real analysis. If you add there are positive numbers, and you define them by the fact that if you add 2 of them, they stay positive. That was quite fun.
Just throwing them in the deep end. Axioms of real numbers. Okay. Let's move on. What's next? Have we got more examples or more?
I think we have one more example.
One more example. Okay. Yeah. Okay.
Yes.
So.
This is a similar example, and and the idea to solve this is pretty much the same as before. We would like to find combinations of a cube, b cube, and c cube on the left-hand side that give us a square b on the right-hand side, and then b square c on the right-hand side as well, and so on, and add them up.
Okay, so
what?
So I've learned to look at the right-hand side of your inequalities, and I can see an a squared b over there. So I've got to imagine how to get an a squared b out of an nth root. It's a real test of indices and powers today, if you're learning that in school. Oh yeah, Alex has got a good point in chat. You should add them if they're the same way round, to make sure. You can add the big sides together, but you can't add a big side to a small side. Okay, I can see an a squared b on the right, so I've got to think about how to get an a squared b out of the nth root on the right. So I guess I'm going to put in something like a to the 2n b to the n. I haven't decided what n is yet. Thinking out loud. Help me out, chat. What inequalities are we adding together? I can get an a squared b if my items multiply to something like a to the 2n b to the n. Don't know what n is. On the left I want them to look a bit like a cubed and b cubed perhaps. So maybe those are what I put in. Raf says 2a plus b. Raf I might steal your idea but put a cubed in instead of a. So if I do an a cubed, another a cubed and a b cubed, that's not the thing on the left, but I think a cubed plus b cubed over 3 bigger than or equal to. I'm going to write this down, I think. Can I write this down? Yeah, let's do this one a little bit. This is literally the speed at which I think, chat. Okay. So I saw there's an a squared b on the right hand side. I've been imagining that as this, where I think maybe n equals 3, because I'm trying to think about having some stuff to add together to be bigger than or equal to the nth root of some stuff, and I want that to magically give me an a squared b on the right hand side. It's pretty hard to hit an a squared b. Raf's suggestion, Alex had said something similar, is that maybe if I put in a cubed twice into the AMGM inequality, so n equals 3, then I'll get out exactly what I want, I think. Sort of like before. Okay, so this is true by AMGM. It's very reassuring, isn't it? When you're doing things with AMGM, it's sort of, you put the stuff in and you get a true fact, which is nice. Okay, so on the left that's going to give me 2a cubed plus b. This is like tick, verified by AMGM. Whether or not it's useful, it's true. Sometimes
you get like inequalities and you don't know if they're going to be useful or not, because AMGM just gives you the power to produce inequalities by plugging in stuff.
I've got an a squared b on the right.
Yeah. And I think that works. But if you do the same thing for the other 3 variables.
Oh, okay. So if I do the same thing, now that I know this is true, I can do the same thing but replacing the letters. And something for C and A as well. And if I add those up, then each letter will appear, I guess, with a 2/3 coefficient and a 1/3 coefficient. So I've got lucky on the left-hand side. Things have worked out. I think this is up here as well.
Yeah.
Yeah. Thank you, chat. Thank you, Etihad. We got that. I still feel. Brilliant. Okay. So I've learned to look at the right-hand side of your inequalities and to see how I'm going to make an a squared b out of that nth root in the AMGM inequality.
Yeah, I mean, sometimes it turns out that like looking at the right-hand side isn't the best idea because like in the examples we have right now, like the left-hand sides are really nice. We have like whole powers and just like pure stuff. Like a cube is pure. It's not like mixed with some other things. But sometimes like we have more mixed things on the left-hand side in some cases where it like if you have something more mixed, it has more information. That's how I like to think of it like that. But it's a bit meta right now. But yeah, as I was saying, like we have a notion of stuff being mixed. And if we look at the previous examples as well, like we'll see that like on the left-hand side, we always have a squared plus b squared plus c squared. And then we have a to the 4 plus b to the 4 plus c to the 4 as well on the other problem. But on the right-hand side, we have mixed variables. Like we are mixing a, b, and then we're mixing a squared and then b, c there. And in general, this holds, there's the fact that like if we have more mixed polynomials, then they have a lower value than if they weren't mixed. And that's called Moorehead's inequality. I originally had that in the slides, but like that we wouldn't be able to do it in the time. So I think we'll have something related to that in the further reading.
I'm going to put Moorehead's inequality in the further reading. Moorehead's gives you a kind of quicker way to generate inequalities that look a bit like the one that we've been doing. But you can just prove them all with AMGM or with the fact that squares are positive if you really want to. That fact right from the start. Okay.
Mm-hmm.
Next slide.
We move on to a non-homogeneous inequality.
Oh, okay. So homogeneous.
Before we do that, I just want to point out that all the inequalities we had before had the same power because they were all polynomial inequalities, and like in the previous example, we had a cube plus b cube plus c cube on the left-hand side, and that had degree 3, and on the right-hand side we had a squared b, b squared c, and c squared a, which had degree 3 as well. So like with all the inequalities we've produced so far with AMGM only holds for equal degrees. Now in this case, they don't really have equal degrees because on the left-hand side we have a squared plus b squared plus c squared, and on the right-hand side we have just a plus b plus c. And if you plug in a squared plus b squared plus c squared in AMGM, you get something like cube root of a squared b squared c squared, and that has degree 2 because we have a squared b squared c squared, and that has degree 6, and then you take the cube root, which has, and then the degree reduces by
it's and there's a cube root. So yeah, it's a kind of if you add up all of the powers, if you replace all the a, b's, and c's with the same letter, then the degrees you get out of AMGM so far have all matched up.
Yeah. And also, like in this example, we have a weird condition that ABC is equal to 1.
And none of the others have had that.
No. And also, like if we didn't have this condition, this inequality would just simply not be true. If, for example, A, B, C were all like 5, then a squared plus b squared plus c squared would be 75, whereas a plus b plus c would be 15. Wait, no, that works.
If they're all really small.
I did the other way around.
If they're all tiny, then the squares.
If they're all tiny,
are tiny,
if they're
right?
all like 0.5, then their sum would be 0.75.
Right. Yeah.
And a plus b plus c would be 1.5, which doesn't hold. Yeah.
Okay, so on the one hand, this doesn't look like something we can do with AMGM so far because the powers don't match up. So whenever you stick stuff into AMGM, it doesn't work out. But on the other hand, we've been given extra information that the product ABC is exactly equal to the mysterious number 1.
And it's equal to 1, and we know that multiplying by 1 doesn't change anything. So we might want to multiply one of the sides. We might want to multiply one of the sides by some power of ABC that makes both of the sides equal in terms of degree.
Okay. Next, yeah.
Yeah.
So your trick, have I got this right? Your trick is to multiply both sides.
Now multiply the right side only.
Oh, right, okay. By a to the multiply the right hand side by a to the 1/3, b to the 1/3, c to the 1/3, because that's secretly equal to 1, the thing you were given in the question. Okay, we can do that, I suppose. That's legal. So you've replaced the thing on the right hand side by a to the 1/3, b to the 1/3, c to the 1/3 times a plus b plus c. That's allowed. Are you claiming that's easier to do than the original question?
Yes. This is going to be easier to do because we have another trick which is going to get rid of all the fractional powers we have now.
Oh, okay. Because I can sort of see that the things on the right now actually feel quite familiar. There's like an a to the 4/3, b to the 1/3, c to the 1/3, which feels a little bit like the stuff we had before.
And then we have like b to the 4/3, c to the 1/3, and then a to the 1/3, and like so on. And on the left hand side we have something simple. Now, if we can get rid of those 1/3 by doing a substitution.
Okay. You're going to get rid of the 1/3. Cool. Okay.
Yeah. So we get rid of the 1/3 by substituting a is equal to x cubed, b equals to y cubed, and c equals to z cubed. And then a to the 1/3 would be just x, b to the 1/3 would be just y, and c to the 1/3 would be just z.
So now that looks a lot like the stuff that we've been doing with AMGM before.
Yeah. Now everything has like equal degree, and we don't have fractional powers anymore, and we can try to apply AMGM to this. Someone asked in the chat that why didn't we multiply both sides by a to the 1/3, b to the 1/3, and c to the 1/3?
Yeah.
Because we can do this because ABC is 1, and also we wanted to make both sides have equal powers, just because we have the intuition that if they have equal degree, then we might be able to do it with AMGM.
Oh, I see. So this term that you're putting in, it's sort of a bit like... So on the left, things are squared. On the right, to start off with, there's just powers of 1. But if you put these thirds in as well, then the total power of each term, if you multiplied out the brackets as well, imagine multiplying out the brackets, the total power of each term will be 1 plus a third plus a third plus a third, which is 2, and it matches up. So now that's why you can now AMGM it or something.
Yes.
If it was... Okay, if it was cubes on the left, I guess you would put 2/3 in, because then that would top it up. 1 plus 2/3, 2/3, 2/3 would be 3. So you could do a kind of cube version of this, I suppose. And then you hit it with AMGM. Brilliant. Okay. Yeah. So Raphael in chat says, wouldn't the a to the 1/3, b to the 1/3, c to the 1/3 just be 1? Yeah. That's why that's allowed, and yet somehow it makes the question look harder, but yet also be approachable with AMGM. Sticking to the AMGM.
We are doing nothing, but also we are doing something to solve the problem.
You got me as well. I think I said out loud, multiply both sides, but because it's the number 1, you're allowed to multiplying things by 1 doesn't change them, so you're allowed to multiply stuff by ABC in this question whenever you like. Which is a bit mad. If you're given that this quite complicated thing is equal to 1, loads of stuff is true as a result, because whenever you see an ABC, it's just equal to 1. So multiplying here doesn't really change anything. It just puts in a 1 to the 1/3 in front of the inequality. Crazy. Okay, I really like this one because it kind of takes a simple looking problem, makes it more complicated, and then hit it with AMGM. Harriet's called that a magic trick. Cool. Brilliant. What's next?
And then like finally we can solve this using the previous trick we had, which is yeah, by AMGM. We use AMGM on. So we have the same. We have a similar thing. We look at the right hand side. We have x to the 4, y to the 1, and z to the 1. So we take 4 lots of x to the 6, 1 lot of y to the 6, and 1 lot of z to the 6, and divide by 6, and use the 6 variable AMGM to get the result. And then we add them up, and everything turns out nice.
Yeah. Okay, I feel like I'm getting the hang of these ones, sticking things in that are the same as each other.
Mm-hmm.
Somebody in chat would like to get crazier. Should we get crazier?
We are going to get crazier.
Okay, so that next slide, yeah?
I think it's the next slide.
Okay, cool. Next inequality.
So like we had a lot of previously while doing AMGM, because we could plug in any n numbers we wanted, any n positive or non-negative numbers we wanted, and we would get an inequality out. Jensen's inequality allows us to do a lot more, because now there's a function involved, and like they have to satisfy a certain condition, which is like being concave or convex. But like if they satisfy the if any function satisfies that property, then for all numbers, all values a1, a2, and so on, we have the following inequality, and this is called Jensen's inequality. But firstly, function is concave. It's the second derivative. Well, it has to exist at first, and then it has to be less than or equal to 0. So, like, if you want to visualize the function, it's like going like this. The second derivative, like the tangent, is always reducing.
It's so first derivative is the gradient, and then second derivative is the rate of change of the gradient.
Yeah, the rate of change of the gradient.
Your gradient is decreasing,
the
like a parabola or something thrown through. For a thing thrown through the air.
And if that is true, then we claim that the following thing is true, which is basically take any numbers and then apply the function, and then take the average of that, and that is going to be less than or equal to if we take the average first and then apply the function.
Wow. Okay.
Now this is quite mouthful.
So on the left, you've got. I'm going to read it out again, sorry, to check I've got it. On the left, you've got all of these different values, a1, a2, up to an, and you're plugging them each into your function, and then adding them together and dividing them. So that's an average of the values.
Yeah. Mm-hmm.
And it's less than or equal to the value at the average.
Yeah.
This is the average of the values, and this is the value of the average.
The average of the values is less than or equal to the average. No. Average of the values is less than or equal to the value of the average.
Right, okay.
Yeah.
Mad. And that's true whenever f is a concave function.
Mm-hmm.
And there's a sort of opposite. You flip the inequalities around for a concave function.
If f is convex, like it being like this, like x squared or something, then the opposite inequality is true. Like I'm not going to say it again because it's really confusing. Average of the values is greater than or equal to the value of the average. In that case, yeah.
Cool. Okay, so this is a massive factory for making inequalities, because so long as we can think of a function that is curved like that, then we can generate new inequalities just by writing this out with our choice of f, function f. Okay.
And you can prove this with just like working with the limit formula of second derivatives. We did that in like our first year maths course, so it's not very easy to do, but also like if you want to, it's a fun exercise. But we're not going to do that as well. But what I will do is show some intuition behind why Jensen's inequality is true. I think that's on the next slide. Yeah. So we have a concave function here, which is sine x. Well, like the important thing to know here is that like sine is not always concave, but it's concave from when x is 0 to pi, and then it becomes convex, and then it becomes concave again, and like so on, which is quite a fun thing. But sine is concave for this image, and if you take 2 points on like the curve, and then take the midpoint of those, and then consider the y value. So the y value of like what's the y value of c here?
I suppose the y value of c
Yeah,
is.
like in terms of like not the exact value, but like what does it represent
So you said c was the midpoint
of a and b?
of this line A and B. I
Mm-hmm.
suppose I could write down the equation of the line, but I guess because of sort of similar triangles or even congruent triangles or something, that C is its y value is halfway up from A to
Yeah,
B.
it's halfway
So
up
I guess it's
between those two.
the average
Mm-hmm.
of the values, right?
Yeah, so the average of the y values of a and b, and the y values of a and b are sine of that point, the sine of a and sine of b, let's say. Um, and so c is the average of the values. And if we just go up in the y-axis, we hit the curve at d, and that's going to be the val. Mm,
That's the value of the function
that's
at
the value of the function at the average.
I think we both regret going on live TV and trying to get the strings average and value the right way around. If you're following at home, the point D is higher up because it's up here at the value of the function evaluated at the average of the values where A and B are, whereas C it's all the way down here. It's at the average of the values between these points A and B. And this is true kind of by the curved shape of the picture that the value of the average is bigger than the average of the values.
Mm-hmm.
Nailed
And it's
it.
also very easy to see that if it was the other way around, if it was flipped and it was convex, then we would have that the average of the values is larger than the value of the average. Um, and like and this holds for like n variables as well. But when you can't really find a geometric interpretation for that. Well, I couldn't. So we're just going to accept that and move on to the problem.
Someone once told me this is a bit like centre of mass, with the n point version. It's a little bit like having n different points on your sine curve and finding their centre of mass. That's a bit
Oh.
like the average. That's to do with the average of where they are. So it's like the average of their values. And because of the sine curve is curved like this, wherever it is, it's going to be inside that curve, the centre of mass, which is going to be underneath, safely underneath the tent of the function. Up here, above that centre of mass, is the value of the function at the average x coordinate. And so the centre of mass is underneath, the average is.
I think Raphael mentioned something like interesting, like this seems very similar to the definition of convexity and concavity, which is very true. Like the reason why this holds is like we have a concave function, and if we draw a line between any 2 points, it will stay underneath, and that's what. And like you can think of like a weighted version of Jensen's inequality where it's not like exactly the average, but you multiply each of the terms by w, where the w's add up to 1, and that still holds. But we like you can do many different generalizations of like inequalities, but and it gets wild. So we're just gonna keep it at a simple level. Yeah.
Sure. Okay, let's do an example.
Mm-hmm.
We got about 10 minutes. I think we've got 10 minutes to do some examples.
Yeah.
That's fine. Okay.
So yeah, this is quite a simple example. Because like Jensen's inequality is so powerful. Like once you choose the right function, it just immediately spills out the inequality. And in this case, there's a very like there's one choice that's like staring at your face.
That's. Just to check, on the right hand side, this is. I should have checked before we went live. This is the number 3 multiplied by the square root, not the.
Yeah,
Yeah,
it's
okay.
multiplied by the square root. Yeah, so it's not the third square. It's not the third square root.
Yeah, not the cube root thing on the right hand side. Okay.
Yeah, sorry, not,
So you've got square roots on the left, you've got square roots on the right, and you would like people in chat to choose a function that's curved like a concave function.
Well, it might be convex because like we have this
the other way
one for
up.
both of the cases. So
Oh yeah.
that would be
Yeah.
the other way around. And like I remember being in an exam where I had to use Jensen's inequality, and I could not remember which way the sign was.
Got to do an example to check the
Yeah.
parity. Yeah, it's the other way up for the. It's the other way round for convex functions. I guess it's sort of
It's the other way around for convex
flip it and
functions.
reverse it. Okay. Let's throw this to chat. What should we use as our function f? We've got this big factory for factory for inequalities, where we just supply it with a function and it gives us inequalities. People have got different picks. Alex missed a bit, and Alex has maybe missed the introduction of Jensen's inequality. It's an anonymous suggestion of square root x. I like Alfie, so Alfie suggested minus x squared, which I think gives us something similar as well. 3 times square root feels very clever because
Okay.
3 times
What
square
does
root,
minus square root
it's got
give
that
us?
3 in it. More suggestions from chat are coming in, so I'm going to give people a minute. There's a bit of lag in between us saying stuff and things appearing on chat. Joe says root x. If you've missed part of the live stream, of course, you can rewind while we're live, or the whole thing is available here afterwards, in perpetuity on our YouTube channel, as well as 30 back episodes. Got a little ad for other episodes. Yeah, I like root x because maybe this is naive, but on the left, root x seems good because it will give me function of each object will give me function of a, function of b, function of c, square root of a, square root of b, square root of c. Add them up, divide by 3, and that's something to do with the thing on the right hand side. I think I like square root x.
Yeah. Well, square. I mean, in fact, like 3 times square root of x works as well.
Oh.
Because like if it's a scalar multiple of square root of x, and I think they both work because the inequality is a scalar inequality. Like you have f on the right side and f on the left side as well, so both of them work.
I'm trying to imagine a squared. I think a squared maybe proves. So if you use f equals squaring, then I think you get a squared, b squared, and c squared on the left, and then I think you prove something a bit like some AMGM stuff.
Yeah.
So hold that thought.
So a square is convex, so it would be the other way around. So
minus
like,
x squared.
Yeah. Well, if you have minus x squared, then we have minus a squared minus b squared minus c squared over 3 would be less than equal to
minus the square of a plus b plus c over 3, which is going to be a bit of a mess to deal with. And I think it's not going to give us a square root like the right hand side. But
yeah.
Okay, so square roots is what you've got on your next slide, I think.
Yeah.
Let's have a quick look at that. So you've checked that the second derivative is negative, so it is concave, we can use Jensen, and Jensen just gives us this, and then cheekily multiply through by 3 to get the thing in the question. Okay, it's pretty nice. Suggestion of cosine. Yeah, okay. People are talking about cosine in chat as well. Your time will come, I think. Next one? Ooh.
Yeah.
This is not an example, this is a proof.
This is a proof. Finally we're going to go like full circle and prove AMGM using Jensen's inequality, and this is quite I find this quite nice because you don't really think Jensen has anything to do with like AMGM because one of the sides of Jensen does have an arithmetic mean, but the other side also has a mean, and you don't know like how you could convert that into a geometric mean. Because there's nothing multiplying stuff. But as I said before, log is a spoiler because like when you log something that has a lot of multiplication, it just becomes additive stuff because you can use the fact that log AB is log A plus log B, and that's exactly what we do here. So we have by Jensen's inequality on log, where we use the function f as log, and if you think of the image of the graph of log, you can immediately see it's concave. Also, you could take the second derivative and get also you could take the second derivative and get that it's minus 1 over x squared, which is concave. Which means that for positive real numbers a1 up to an, Jensen's inequality gives us this. And f here is log, so we could just apply log here. So on the left hand side, we have log of the average is greater than or equal to log of each of the elements and divided by n. And then we use the property of log that we know on the right hand side. So I've done both of the same in the same one. So I'll just go through it slowly. So we bunch up all the logs together to get like log of a1 times a2 times a3 and so on up to an and over n. And since we are multiplying by 1 over n, we can, like by properties of log again, take that inside the log by taking the nth root, and that's basically what we have in the last line. And finally, we have log of the arithmetic mean is greater than or equal to log of the geometric mean, and we can just take exponential of both sides to get the AMGM inequality, which is quite neat.
It's so nice. This step, by the way, the one that we got people to do at the start of the show for the case n equals 2. They did it, I guess, this way around, going from here to here to rearrange stuff. This is one of the things I love about Jensen's inequality, is that you can pick your function log of x, and then it just generates not just one inequality, it generates the entire AMGM inequality from the start of this session, which just is itself really handy and lets you do lots of different things. So Jensen's inequality contains within it multitudes of different stuff. Cool. At least 1 or 2 people in chat have just learnt that the derivative of log x is something that people know, and I think you learn at some point during A-level maths. Derivative of log x is pretty nice. 1 vote from Harriet for that proof is awesome, of just combining together choice of f. We've gone really quickly through a couple of examples, but there are lots of other things you can try. People who said cosine and sine and stuff in chat can generate their own cool inequalities to do with like sine of some stuff or whatever. Okay, last thing I think is the generalization of AMGM.
Yeah, this is very this is quite not a notation. Like it took me like 30 minutes to figure out the bracket. But yeah, so this is a different, like since we can prove AMGM by Jensen, you can say that like Jensen is like a generalization of AMGM. This is a different kind of a generalization, which is we have this function p of r, which is basically if r is non-zero, we multiply each number by, we take the r's power of each number and then add them all up, divide them by n, and then take the rth root. So if r was 1, we would just add, we wouldn't have any power or taking roots, so we would only have the arithmetic mean. If r was 2, we would square each of the numbers, divide by n, and then take the square root. And that turns out to be the quadratic mean, and the root mean square, which I think is used in statistics. Yeah.
Other inequalities are available. I love this one because it's cool.
And then, like, if r is 0, we just define the p of r to be the geometric mean. And there's a like nice reason for that, is because like if we take the limit of r tends to 0, then we get this value for any like any positive real numbers a1 up to an, and that's why we define it to be like that. And it turns out that like for any real numbers r and s, if r is greater than s, then p of r is greater than p of s, which is really wild because now we have families of inequalities on top of each other. for every positive real number, we have an inequality. So it's like uncountably many inequalities on after the other. But like if we take r equals to 2, we get the quadratic mean. If we take r equals to 1, we get the arithmetic mean. And then for r equals to 0, we get the geometric mean. And for r equals to -1, we get the harmonic mean. And these 4 means are like quite useful in like maths and physics. So these ones have names, but I think the higher ones are called moments.
Oh right, yeah, I've heard about these of adding up things for
Yeah,
higher values.
there's something to do with
Powers and
moments,
things.
but I'm not really sure. Yeah, so like there are really cool proofs online about how of the like QM, AM, GM, HM, uh, like chain. But yeah, that's basically I think what we had today.
Brilliant. Thank you very much. I'd like to leave leave the live stream on a note that means that future me has to write loads of stuff into the further reading. So stuff
Yeah,
on loads of hooks of extra bits of inequalities and other puzzles to try perhaps coming in a further reading tomorrow on the Maths Club website. I want to leave with a puzzle as well because somebody suggested one thing. We're going to overrun very slightly. This is part of my running theme of trying to crowbar dice into the Oxford Online Maths Club. So here's another OOMC dice problem. A couple of weeks ago, we talked about on the live stream working out what would happen if you roll 2 dice and take the higher number for perhaps for n-sided dice. N-sided because we're nerds and we would like to know about 6-sided dice, but also 20-sided dice, and somehow doing the algebra with n feels easier than doing it twice for 6 and 20. Since then, I've been talking to some of the people from the club who've emailed the Maths Club email address, which is on the Maths Club website, and possibly in the bit of YouTube below, to talk about 3 dice instead, or even 4 or 5 or k dice. The idea, by the way, is that when you roll 2 dice and take the higher number, the expected thing that happens, the kind of average for 2 dice, is bigger than the average. I guess I'll put a, for the theme today, I'll put a bigger than or equal to. If you just rolled 1, in fact, you can do a lot of algebra to show that the average, if you roll 3 dice, is bigger than the average when you roll 2 dice and take the highest number. So again, 3 dice and take the highest number, 2 dice and take the highest number is bigger, but the function k average, the function is concave. So the amount that it increases decreases each time. So there's your link back to some dice problems to try. There's some inequalities about how this thing increases, and the function itself for the average over k dice being rolled is concave. You have diminishing returns. Thank you very much for joining us today, everyone in chat. And of course, thank you to Idiad for joining in with Inequalities. That was a lot of fun. Thanks for coming along again for your 3rd appearance on Oxford Online Maths Club. We're going to be back same time next week for another episode. And I'll see you then. Take care, everyone. Have a nice evening. Bye.